Name the type of protein structure in figure 3. So what have you actually got? So within the chain itself would be a primary structure, but you've got bonds between different sections of the chain. So you've got bonds here, so that's a secondary protein, because you've got bonds between the actual chain itself. So if then you had bonds between one of these and another one, it would be tertiary, and then if you have them in layers and pleats, then it's quaternary. But here, so it's not just bonds within the chain, you've actually got bonds between different sections of the chain, so that's secondary. I think this bit's tough here. Explain the origin and the interaction represented by the dotted lines in figure 3 for 4 marks. We're looking for 4 things. So what have we got here? We've got a C to O bonding to an N to an H. So you need to say that the N to H is polar, so there's a slight minus, a delta minus on the N and a delta plus on the H. And similarly here, you've got a delta plus on the carbon, a delta minus on the O. I think for a second mark then you'd say that the O and the N are electronegative, that's why they get small delta minuses. That then you've got an N bonded to an H, so you've got hydrogen bonding. So if you've got an H bonding to an N, an F or an O, then you've got hydrogen bonding. And probably finally that you've got a lone pair of electrons on the O here, which is attracted to the delta plus for the 4th mark. A tricky question this. N and O are electronegative, so they get a slight delta minus. It creates polar bonds, delta plus and delta minuses between the C and the O and the N and the H. Hydrogen bond between the O and the H, because you've got an N to an H there, so that's a large difference in electronegativities. Anytime you get an H to an N or an H to an O or an H to an F, you get a very, very large polar bond there, a large delta plus on the H, and that's going to attract the lone pair of electrons on the O very strongly and create a hydrogen bond.